Here is the result that sets the tone for this entire video. A perceptron, the simplest possible neural network, a single artificial neuron, is trained on real clinical data to detect liver disease. Its test accuracy is 65.1%. A majority class baseline, a model that predicts the most common outcome for every patient without looking at a single feature, reaches 71.2%. The neural network loses to a rule that does not learn. That result is the point. Deep learning is not magic. It is not automatically better because it sounds more advanced. At its foundation, it is still a model trying to separate signal from noise. When the signal is weak, the features are limited, or the data does not support the complexity. A neural network can fail, just like any other model. This video builds deep learning from the ground up, from a single perceptron to hidden layers to multi-layer networks. Not to make the models seem mysterious, but to show exactly when that extra complexity helps and when it hurts. Many practitioners encounter deep learning from the top down. Large language models, image classifiers, generative AI systems, and impressive demos. They see the output and assume the mechanism is fundamentally different from the machine learning tools already covered. It is not. Deep learning is built from simple parts: inputs, weights, bias terms, activation functions, errors, and updates. The right way to understand it is from the bottom up. Start with one artificial neuron. Learn what it can represent. Watch where it fails. Then add hidden layers only when the limitation is clear. That is the discipline behind this video. A 10-layer network is not easier to understand by staring at all 10 layers at once. It becomes understandable only after the first layer, the first activation, and the first failed boundary make sense. The bottom-up path is slower. It is also the path that separates real understanding from simply running someone else's code. A perceptron is the simplest possible learning unit. It takes input features, multiplies each feature by a learned weight, adds them together, includes a bias term, and passes the result through a threshold. The output is binary: disease or no disease, phishing or legitimate, class 0 or class 1. During training, the perceptron makes a prediction, compares that prediction to the correct answer, and updates its weights when it is wrong. The rule is simple. Move the weights in the direction that would have made the correct prediction more likely. That is the foundation. A perceptron draws one linear decision boundary through the feature space. One straight separation. One attempt to divide the problem into two sides. Everything that comes later, hidden layers, nonlinear activation functions, backpropagation, and the architecture of modern deep learning, is a structured response to one problem. What happens when one straight line is not enough? Passing the OpenML Indian liver patient dataset through a perceptron classifier in a pipeline using both categorical and numerical features is worth examination. The test set is imbalanced: 104 disease cases and 42 non-disease cases. A perceptron with balanced class weights reaches 65.1% accuracy. The majority class baseline reaches 71.2% by predicting disease for everyone. And the most important number is not accuracy. It is recall for the disease class, the sensitivity that matters in a clinical screening context. That recall is approximately 63.5%. In practical terms, the model misses roughly 1 in 3 sick patients. The pipeline is not the issue. The training process is not the issue. The result is reproducible. The issue is that the feature set, the class imbalance, and the perceptron's linear decision boundary combine to produce only modest discriminatory power on a task that demands much more. This is where the lesson becomes practical. A perceptron is not wrong because it is simple. It is wrong when the problem requires structure that a single, straight boundary cannot capture. Recognizing that early instead of endlessly tuning a model that does not have enough expressive power, is what separates applied machine learning from simply running code. The OpenML phishing websites dataset tells a completely different story. This time, the Perceptron is not being asked to separate weak clinical signal with a limited linear boundary. It is being applied to categorical URL, host, and page features that are directly tied to phishing behavior. SSL state, anchor patterns, prefix and suffix indicators, DNS records, web traffic signals, links pointing to a page, shortening services, IP address usage. These are not abstract measurements, they are operational clues. The pipeline one-hot encodes the categorical features, balances the classes, trains a perceptron, and compares the result to a simple majority class baseline. The baseline accuracy is 55.7%. The perceptron accuracy is 94.1%. That is an absolute improvement of roughly 38 percentage points. This is the contrast that matters. On the OpenML Indian liver patient dataset, the perceptron failed to beat the majority baseline. On the OpenML phishing websites dataset, the perceptron dramatically outperforms it. Same foundational model, very different data geometry, very different outcome. The classification report makes the result even clearer. For legitimate websites, the model reaches 0.912 precision, 0.958 recall, and 0.935 F1. For phishing websites, it reaches 0.965 precision, 0.927 recall, and 0.946 F1. That means when the model flags a site as phishing, it is usually correct. And when a site is legitimate, the model usually lets it pass without unnecessary friction. The confusion matrix shows the operational trade-off. Out of 1,225 legitimate sites, only 51 are incorrectly flagged as phishing. That is roughly 4.2% of safe sites blocked. Out of 1,539 phishing sites, 113 are missed. That is roughly 7.3% of phishing sites slipping through. Neither error disappears, but both are low enough to make the model practically useful, especially compared with a naive rule that simply follows the majority class. The coefficient chart explains why the perceptron works so well here. Large positive weights push the decision toward phishing. Features such as suspicious URL anchor behavior, abnormal SSL state, prefix-suffix patterns, DNS record indicators, low web traffic, shortening services, and IP address usage all push the model toward the phishing class. Large negative weights push the decision toward legitimate. The complementary feature states move the prediction in the opposite direction. That is exactly what an interpretable security model should provide. Not just a prediction, but a reasoned directional signal. The model can say, in effect, these website characteristics are pushing the decision toward phishing, and these characteristics are pushing it back toward legitimate. That matters in production. A security team does not only need accuracy. It needs a model that can be audited, explained, challenged, and improved. A two-dimensional SVD plot is useful, but only as a warning. When the full one-hot encoded feature space is compressed into 2 dimensions, the visualization model reaches only about 53% test accuracy. That does not contradict the main result. It shows that the real separability lives in the high-dimensional categorical representation, not in the flattened 2-dimensional picture. The plot is a teaching aid, not the production model. The learning curve reinforces the same lesson. Training and validation accuracy track closely, usually around the low 90s, which suggests low variance and reasonable generalization for a linear classifier on this feature set. More data can still help, but the main signal is already strong. This is what it looks like when a simple neural model is the right tool. The perceptron succeeds here because the features are structured, categorical, and meaningfully aligned with the decision. The boundary may be linear, but in the expanded one-hot feature space, that linear boundary is powerful enough. So the lesson is not that perceptrons are weak, and it is not that deep learning is automatically better. The lesson is sharper than that. Model complexity only helps when the data demands it. On the OpenML phishing websites dataset, a simple Perceptron pipeline is high-performing, interpretable, and defensible. That is applied machine learning done correctly. The next example makes the Perceptron's limitation visible. Using the OpenML oranges versus grapefruit dataset, the task is to distinguish two kinds of fruit using diameter and weight. That sounds simple, but the feature space is not perfectly clean. Some oranges are larger, some grapefruits are smaller. The two classes overlap along the same diameter-weight pattern. A single-layer perceptron can only draw one straight boundary through that space. In the decision boundary plot, that is exactly what happens. The perceptron splits the scaled diameter and weight space with one linear cut. It performs well, reaching about 95.1% accuracy on the held-out test set. But its errors cluster near the overlap, where the two fruit types are not cleanly separable by one line. Then, the same task is given to a multilayer perceptron. Same dataset, same two visualized features, same train test split. But now, hidden layers are added between the input and output. The MLP reaches 97.6% accuracy. That is a gain of about 2.5 percentage points. On a 3,000 example test set, that means the perceptron gets roughly 2,852 examples correct, while the MLP gets roughly 2,928 correct. That is 76 additional correct predictions from the same two features. The error rate drops from about 4.9% to about 2.4%, roughly a 51% relative reduction in error. That is the point of hidden layers. Not mystery, not magic. Function approximation. The MLP does not draw one straight line. Its decision surface bends. In the plot, the boundary forms a wedge around the region where the fruit classes overlap. That curvature captures structure the perceptron cannot express. This is what hidden layers do. Each neuron takes weighted combinations from the previous layer, applies a nonlinear activation function, and passes the result forward. One layer learns simple transformations. Additional layers combine those transformations into more flexible representations. Stacked together, they allow the model to represent curved boundaries, interactions, and nonlinear patterns that a single perceptron cannot capture. But the gain is earned, not assumed. The perceptron was already strong on this task. The MLP helped because the remaining errors were concentrated in a region where the linear boundary was too rigid. That is the key distinction. Deep learning helps when the problem contains structure that simpler models cannot represent. It hurts when extra layers add complexity without adding useful signal. So the question is not, should a neural network be used? The better question is, what limitation is the next layer solving? Once one neuron fails, the next question is, what happens when neurons work together? That is the idea behind a multi-layer perceptron. A single perceptron sees the original inputs and tries to draw one boundary. A hidden layer does something more powerful. It learns combinations of those inputs. Think of a weather forecasting team. One person watches temperature, another watches humidity, another tracks air pressure. Individually, each signal can support a rough guess about rain, but the real pattern appears when the signals interact. Warm temperature by itself does not mean rain. High humidity by itself does not guarantee rain. Falling pressure alone is incomplete. But warm air, high humidity, and falling pressure together can indicate that rain is likely. The interaction carries the signal. Hidden layers work the same way. Each neuron takes weighted inputs from the previous layer, applies an activation function, and passes a new transformed signal forward. The first hidden layer may detect simple combinations. Later layers combine those combinations into more sophisticated patterns. That is how an MLP captures thresholds, interactions, curved boundaries, and latent structure that the raw input features do not express directly. Activation functions make this possible. ReLU, the rectified linear unit, is one of the most common. It outputs 0 for negative inputs and passes positive inputs forward linearly. That simple rule introduces nonlinearity. And nonlinearity is the entire reason stacking layers matters. Without activation functions, multiple layers collapse mathematically into one linear transformation. In other words, stacking linear layers without nonlinear activation does not create real depth. It only disguises one straight-line model as a deeper network. The activation function is what lets each layer reshape the feature space before the next layer receives it. That is why hidden layers are not magic. They are learned feature combiners. They build internal representations that help the model express relationships the original features could not express on their own. But this power has a cost. More layers mean more parameters. More parameters mean more capacity. And more capacity means more opportunity to memorize noise instead of learning durable structure. That is why neural networks need safeguards. Regularization to discourage extreme weights. Early stopping to halt training before memorization takes over. And careful learning rate control so updates do not overshoot or stall. Depth makes a model more expressive. It also makes the model easier to misuse. The goal is not to add layers because deep learning sounds advanced. The goal is to add layers only when the problem contains interactions that simpler models cannot represent. A rain prediction example gives the direct comparison this video needs. Using the OpenML weather dataset, the task is to predict whether it will rain tomorrow from meteorological features such as minimum temperature, maximum temperature, humidity at 3 p.m., pressure at 3 p.m., and temperature at 3 p.m. This is no longer a clean toy problem. The dataset contains 142,193 records. Only 22.4% of examples are labeled as rain tomorrow, which creates a moderate class imbalance. Important features also contain missing values. Humidity at 3 p.m. has more than 3,600 missing entries. Pressure at 3 p.m. has nearly 14,000 missing entries, and those are not minor variables. Humidity and pressure are two of the most meteorologically meaningful signals in the task. So the workflow has to be practical. Impute missing numeric values, standardize the features, preserve the train-test split, and compare models honestly. 3 models are evaluated: a majority-class baseline, a single-layer perceptron, and a multilayer perceptron with hidden layers, ReLU activations, L2 regularization, early stopping, and adaptive learning rate scheduling. The baseline achieves 77.6% accuracy. At first glance, that sounds strong, but its balanced accuracy is 50%, and its precision, recall, and F1 for rain are all 0. It simply predicts no rain every time. That is not forecasting. That is class imbalance hiding failure. The perceptron changes the behavior completely. Its overall accuracy drops to 71.6%, but its balanced accuracy rises to 72.7%. More importantly, its recall for rain reaches 74.6%. The perceptron catches most rain events, but it does so aggressively. The confusion matrix shows 7,137 true rain detections, but also 9,698 false alarms, where no rain days are predicted as rain. This is a model that overwarns. In some contexts, that may be acceptable. If the cost of missing rain is high, such as drought planning, field operations, or outdoor logistics, a model that catches most rain events may be preferable, even if it raises more alarms. The Perceptron also gives an interpretable view of the decision. Humidity at 3 p.m. has the strongest positive weight toward rain. Maximum temperature has a strong negative weight. Pressure at 3 p.m. also pushes negatively. That aligns with physical intuition. Humid, lower pressure conditions are more consistent with precipitation, while hotter, drier conditions often reduce rain likelihood. This is the advantage of the linear model. Its behavior is easy to inspect. The MLP improves the overall ranking and the cleanliness of positive predictions. Its accuracy rises to 83.9%. Its precision for rain reaches 73.4%, and its rocker improves from 0.805 for the Perceptron to 0.842 for the MLP. Across thresholds, the deeper model is better at ranking rain risk. The training loss curve also shows the MLP learning smoothly, a sharp early drop, followed by gradual stabilization as adaptive learning rate scheduling reduces the step size when progress plateaus. But the MLP does not simply win. It changes the trade-off. The confusion matrix shows that false positives collapse from 9,698 with the Perceptron to 1,528 with the MLP. That is a dramatic reduction in unnecessary rain alerts. But rain recall falls from 74.6% to 44.1%. The MLP misses 5,346 rain events. The Perceptron missed 2,426. So the deeper model is cleaner, more precise, and better ranked overall. But it is also less sensitive to actual rain events at the chosen threshold. That is the core lesson. Depth helped. The MLP captured nonlinear interactions among humidity, temperature, and pressure that the single straight boundary could not represent. But depth did not remove the need to define the operational objective. For alert fatigue, the MLP may be better because it avoids too many false alarms. For safety-critical planning, the Perceptron may be better because it catches more rain. And for deployment, the right answer may be neither default threshold. It may be threshold tuning against a real cost function. This is what deep learning looks like in practice. It does not replace evaluation. It intensifies evaluation. Adding hidden layers can improve performance, but it can also move errors from one category to another. The question is not whether the deeper model has the better headline accuracy. The question is whether its mistakes are the mistakes the application can tolerate. After seeing hidden layers improve performance, the next question is obvious. How does the network learn those internal patterns in the first place? The answer is backpropagation. Backpropagation is the feedback system that teaches a neural network how to adjust its weights after making mistakes. Think of a coach reviewing a team after a game. The final score tells whether the team won or lost, but the coach does not stop there. The coach looks backward through the game and asks where the outcome came from. Which pass was missed? Which decision created pressure? Which player was out of position? Which adjustment would improve the next play? Backpropagation does something similar inside a neural network. First, the model performs a forward pass. Input data move through the network layer by layer. Each neuron takes weighted inputs, adds a bias, applies an activation function, and passes its output forward. By the end of that process, the network produces a prediction. Rain or no rain? Phishing or legitimate? Orange or grapefruit? Then, the model compares that prediction to the correct answer. The difference becomes the loss. Loss is the model's error expressed as a number. A high loss means the prediction was poor. A low loss means the prediction was close. Then comes the backward pass. The network sends the error signal backward through its layers. Each connection receives feedback about how much it contributed to the mistake. The point is not to blame one neuron for everything. The point is to distribute responsibility across the entire chain of weights and activations that produce the final prediction. Once that responsibility is estimated, the model updates its weights. Each weight is nudged slightly in the direction that should reduce future error. The learning rate controls the size of that nudge. If the learning rate is too large, the model can overshoot good solutions. If it is too small, learning becomes painfully slow. That is why adaptive learning rate scheduling matters. When improvement slows, the step size can shrink, allowing the model to make finer adjustments instead of bouncing around the solution. This cycle repeats again and again. Forward pass, calculate loss. Backward pass, update weights. Another epoch, another pass through the training data. Early in training, the loss often drops quickly because the model is correcting obvious mistakes. Later, improvement slows as the model makes smaller refinements. When the loss stabilizes and performance stops improving meaningfully, the model has converged. That is backpropagation without calculus. It is not magic, it is structured self-correction. The model makes a prediction, measures how wrong it was, traces that error backward, and adjusts the internal connections that shaped the mistake. This is what allows multi-layer networks to learn patterns that were never explicitly programmed. No one writes a rule that says exactly how humidity, temperature, and pressure should interact. No one hand codes every suspicious URL pattern. The network learns those relationships by repeatedly receiving feedback and adjusting its internal representation. But this also explains why deep learning can be fragile. In deeper networks, feedback signals can become too weak to matter or too large to control. Those are the simplified ideas behind vanishing and exploding gradients. If the signal fades, early layers stop learning effectively. If the signal grows too aggressively, training becomes unstable. Activation functions, regularization, early stopping, and learning rate scheduling are practical tools for keeping that feedback process controlled. Backpropagation is the engine of deep learning. But like any engine, it needs the right fuel, the right constraints, and the right operating conditions. Without meaningful signal in the data, backpropagation only learns noise faster. With the right structure, it turns mistakes into progressively better representations. The same ethical principle appears throughout deep learning. As model depth increases, predictive power may improve, but transparency usually decreases. A perceptron is readable. Its weights can be inspected directly. A positive coefficient pushes the prediction toward one class. A negative coefficient pushes it toward the other. That does not make the model perfect, but it gives the practitioner a clear line of explanation. A stakeholder can ask, why did the model make this decision? And the answer can begin with concrete feature influence. Humidity pushed the model toward rain. Higher temperature pushed it away. A suspicious anchor pattern pushed the model toward phishing. A legitimate SSL pattern pushed it back. That kind of explanation matters. A multi-layer perceptron is different. Hidden layers learn internal representations that are not directly human-readable. Each neuron transforms the outputs of earlier neurons. Later layers combine those transformations again. By the time the final prediction is produced, the decision reflects many learned interactions across weights, activations, and layers. There is no single coefficient table that fully explains the model. That opacity is not automatically unacceptable. In low-stakes domains, such as classifying fruit images, recommending visual categories, or optimizing a non-critical workflow, the performance gain may justify the reduced transparency. But in high-stakes domains, the standard changes. Healthcare, credit, employment, education, criminal justice, public benefits. Any setting where automated decisions affect access, opportunity, safety, or freedom requires a higher burden of justification. A deeper model must be documented. Its data sources must be understood. Its error patterns must be audited. Its thresholds must be justified. Its predictions must be reviewable. And its use must be tied to a real need that a simpler model could not satisfy. Post hoc explainability tools can help. SHAP can estimate how features contributed to a prediction. Permutation importance can show which variables matter most to performance. Error analysis can reveal where the model fails. Calibration can test whether predicted probabilities behave like real probabilities. But these tools do not erase the transparency trade-off. They explain around the model. They do not turn a deep network into an inherently interpretable one. That distinction matters. Deep learning helps when the problem is genuinely non-linear. The data supports the complexity, and the deployment context can tolerate reduced interpretability. It hurts when complexity is added before the objective is clear. It hurts when a model becomes harder to explain without becoming meaningfully better. And it especially hurts when the people affected by the model cannot challenge, understand, or appeal its decisions. The responsible question is not just, can a deeper model perform better? The responsible question is, does the gain justify the loss of transparency? Chapters 8 and 9 of my book Applied Machine Learning, Concepts, Tools, and Case Studies walk through all of this with working code. The OpenML ILPD and phishing websites Perceptron pipelines. The oranges versus grapefruits boundary comparison. The full rain prediction case study with Perceptron and MLP side by side. Backpropagation explained without calculus. And the ethics notes on depth and transparency. If you want to understand deep learning from the foundation up, the link to my book is in the description. With the foundation of neural networks established from first principles, the series is ready to move into the architectures built on top of it. Convolutional networks for images, recurrent networks and transformers for sequences, and the applied case studies that show where each earns its complexity. That is where the series heads next. Deep learning is not the answer to every problem. It is the answer to problems where the structure is genuinely non-linear, the data is sufficient, and the interpretability trade-off is acceptable. Earn the complexity before you claim it. See you in the next video.